So in our last unit we studied balanced forces. So for example, here I am. I'm standing on a scale. And I have the scale reading. Well, what does the scale actually tell me? I know that I have a weight that points down. I know that I have a normal force pointing up. And these two forces balance. And what that means is that the normal equals the weight. The way I like to write this is that the normal force minus the weight equals 0. And so when I read a scale, it's actually, strictly speaking, not reading the force of pulling from gravity. This normal force is actually what the scale reads. We did an elevator lab today. And what we did with this elevator lab is we basically looked at an elevator in several situations and said, well, what actually happens? Now, what we mean by what actually happens is we know the elevator starts at rest, it accelerates upwards, goes up at a constant velocity, slows down, stops for a second, speeds up to get going downwards, coasts at a constant speed, and then stops. And the question we want to ask ourselves is, well, when the forces are balanced, there's really no question to ask. We're at rest. That would mean the normal and the weight are totally balanced. Constant velocity upwards, normal and weight are balanced. At rest at the top, normal and weight are balanced. Accelerating downwards, oh, not. But constant velocity downwards, normal and weight, definitely balanced. Now, when we look at the even-numbered situations here, situations 2, 4, 6, and 8, we don't meet the criteria of balanced forces. Because in our last unit, what we learned is forces balance when things don't move or when we are at constant velocity. And well, when we go back to our lab, all the even-numbered situations involve velocity changing. So, what does it take for an elevator to accelerate upwards? It means the normal force has to be much bigger than the weight in order for it to accelerate upwards. Well, not much bigger, but visibly bigger, because there's a tug of war, and to accelerate upwards, the normal force must overcome the weight in order to force the elevator upwards. When we slow down as we approach the top, well, that means I'm trying to get pulled back down. So that means the weight must point down. The normal force must be less. Continuing on, when I accelerate downwards, well, the weight is clearly trying to pull the elevator downwards. It's more powerful than the normal force, so it would be bigger. And when we slow down as we approach the bottom, there, the weight wants to pull us down. We don't want to keep going downwards, so the normal force had better be bigger than the weight in order to balance that out. So those were the measurements that we made in the elevator. And what actually ended up happening was that we got to a place where we said, well, what's happening with the forces? In the old unit, when they were balanced, well, when we added up all our forces, the effect was nothing. In the new unit, what's actually happened is we've reached a point where we say, add up all the forces, and the effect is the mass, that's the object. It speeds up, slows down, or changes direction. Well, we call that acceleration. So the fundamental equation of today's lab is that the forces acting on an object make the mass accelerate. The specific application to this work, if you go to the problems. So here's how I actually apply this equation. Let's take a look at problem number 6 in your yellow packet. So for example, if I have an elevator that accelerates upwards when it first starts moving and I want to know the normal force, let's say that I'm a person who weighs 800 newtons, and that's going to make my mass about 82 kilograms. Well, the way I specifically apply the unbalanced forces that make my mass accelerate to this problem is I have the normal force. It competes with my weight, and the effect is my 82 kilograms undergoes an acceleration of 0.25 meters per second squared. So when I actually go ahead and solve for my normal force, I will actually get 800 plus 0.25 times 82. Well, in short, I'm getting a normal force of 820.5 newtons. Now, does this match our experience? Look at your lab. we're saying that when we accelerate upwards, we first start moving upwards, the normal force should actually read heavier than the scale, because the scale is only going to read 800 newtons for my weight. At rest, is the normal force bigger? That's the question you have to ask yourself by looking at your lab data. So this is basically an introduction to what the point of the lab was, and we're going to actually take this up a little bit more in class next time.